One other thing that I wanted to mention about the equilibrium constant, capital K, is that when you have a gas phase reaction, so when the reaction components are all gases, then you often see equilibrium constants written in terms of pressure units instead of concentration units. And so we would call that equilibrium constant capital K with a subscript P or Kp. It's important that you know if it's a Kp or a Kc because the equilibrium constant doesn't have units, and therefore you need to know which equilibrium constant you're using in order to know which values to plug in. So the equilibrium constant expression is still very, very similar, except we don't use concentration units, we use pressure units. And so if we start with our generic reaction like we did before, where the lowercase letters are stoichiometric coefficients and the uppercase letters are reaction components, and so compounds or molecules or atoms that participate in the reaction, then we can write our equilibrium constant expression for Kp as the partial pressure of gas C raised to the lowercase c power times the partial pressure of gas D raised to the D power divided by the partial pressure of gas A raised to the A coefficient that raised to that power, and then the partial pressure of gas B raised to its stoichiometric coefficient. The P here, if this were in the, this signifies that pressures are used. If there's no subscript given, then it's assumed to be a Kc, the concentration units. So when pressures are used, there's always a Kp included there. So these are partial pressures, which if you go back to your Chem 101 notes or those sections of the book, remember that when you have a mixture of gases, the pressure that each part of the mixture, each pure gas exerts overall is called the partial pressure. The total pressure is the sum of all the individual partial pressures. And you also would have learned that the partial pressure of a given gas is equal to the total pressure times the mole fraction of that gas in the mixture. So you've learned about partial pressures already. If you need any help with that, please let me know. These would be in pressure units, usually atmospheres. And remember that the lowercase letters are the stoichiometric coefficients. Those become powers just like they are in the Kc expression, right? So these lowercase letters A, B, C, and D become powers in the Kp expression. Okay, so let's just do a couple of practices, make sure people know how to do this. So you can see the generic reaction up here and the Kp expression for a generic reaction. So if we practice for these two, we have 2 moles of ozone reacting to form 3 moles of oxygen in the first reaction, and then we have 2 moles of CO2 reacting to form 2 moles of carbon monoxide and 1 mole of oxygen. So the one on the top, you're going to get a Kp expression where you have the partial pressure of oxygen cubed because of that 3 coefficient, divided by the reactant ozone, partial pressure of ozone squared, and then the lower reaction, we're going to have the partial pressure of carbon monoxide squared times the partial pressure of oxygen to the first power, divided by the partial pressure of CO2 squared in the denominator. Now, I wanted to also explain there's an equation that allows you to interconvert Kp and Kc. They are not necessarily the same value. We'll talk about in a minute when they are the same. But there's an equation to interconvert them, and I wanted to show you how you derive that equation. It isn't really very complicated. These are the two expressions, the one on the left for Kp and the one on the right for Kc. If we use the ideal gas law and we solve for pressure and we plug that into Pa, Pb, all of that in the Kp expression, then that will allow us to discover the mathematical relationship between Kp and Kc. So remember the ideal gas law, PV equals nRT. If we solve for P, we get this expression, P equals nRT over V. Remember that N over V is the same thing as molarity, right? N is moles and V is volume, so N over V is moles per liter. So N over V is the same as molarity, and that's what the brackets are in the Kc expression. So molarity, the molarity of C would be C in brackets, which is moles of C divided by volume of C. So if we then plug N over V times RT in for all of our pressures, right? So remember that N over V is the same as concentration, so we're going to plug those in. You end up getting this for our Kp expression. So this is because I've plugged in the pressure of C, which is really molarity of C times R times T, and that's all raised to the C power, because remember the partial pressure of C is raised to the C power. And we plug the same thing in for D, and the same thing in for A, and the same thing in for B, then, and you rearrange it a little bit, remember the brackets mean Kc, so if we rearrange that, we get that C raised to the C power times D raised to the D power times A raised to the A power times B raised to the B power. If we put all those together, that's really the same thing as our Kc expression. And so now we end up with the equation Kp equals Kc times RT raised to the delta N. Delta N is the difference in the number of moles of gaseous products minus the number of moles of gaseous reactants. So now you can see that Kp will equal Kc as long as the moles of gas on the left and the right are the same. So this is the equation that you will use to convert between K values. And I think probably the most important thing is to remember, to keep in your brain, is that if the moles of gas are the same on the left and on the right, then you end up with a Kp equal to Kc.